And now for the last talk of our session, Satoshi will talk about weakest preconditions.
Okay, so I'm going to talk about my work on weakest preconditions and CPS transformation. So this is the overview of my talk. So the problem we considered is how can we syntactically compute generic weakest preconditions. We considered this problem because syntactic computation would be more useful for program verification. And we obtained two results. One is a general theorem, and the other is instances of the general theorem. So before explaining these results, let me start from the motivation and background. So the motivation is, we want to syntactically compute generic weakest preconditions. But first of all, what are weakest preconditions? So I would say weakest preconditions are something that enable us to reason about programs backward. So here, backward means from output to input. Okay, so suppose we have a program, and we consider a condition that should be satisfied by an output of the program. And this is called a post-condition. So in other words, a post-condition is a function that takes an output and returns a truth value. And then we consider the condition on input under which the output of the program satisfies the post-condition. And this is called the weakest precondition. Okay, so I'm going to show you several instances of weakest preconditions. And the first one is the weakest precondition for pure programs. So for simplicity, let's consider a very simple program which takes an integer x and returns x squared. And as a post-condition, consider the condition that output y is no less than 4. And in this case, the weakest precondition is given by this condition. This is because an output of the program satisfies the post-condition if and only if this condition, an input satisfies this condition. Okay, next, so let's consider more realistic programs. So if a program may not terminate, then we need a slightly different definition of weakest preconditions. So for example, consider this program. So this program computes the factorial of x if x is non-negative. And if x is negative, this program diverges. And in this situation, there are two possible ways to define weakest preconditions, depending on whether we consider the post-condition satisfied or not when the program diverges. So if we consider that the post-condition is not satisfied when the program diverges, then the weakest precondition is given like this. This is called the weakest precondition for total correctness. And this condition basically says that the program terminates and the output satisfies the post-condition. And on the other hand, if we consider that the post-condition is satisfied if the program, when the program diverges, then we get the weakest precondition for partial correctness. And the weakest precondition for partial correctness says that either a program diverges or the output satisfies the postcondition. Okay, so far, we have seen some classical instances of weakest preconditions. And they use Boolean values as truth values. But there are also other instances which uses non-Boolean value as truth values. For example, if we consider, if we use extended non-negative real numbers as truth values, then we can define the weakest precondition for expected cost of probabilistic programs. And if given so if we use a set of states of finite automaton as a truth value, then we can also define the weakest precondition for trace property. So I'm going to explain more about these instances. Okay, so now let's consider a probabilistic program like this. So this program is a program that keeps tossing a biased coin until a head comes up for the first time. And the problem here is what is the expected number of tosses? What is the expected number of tosses? And in this situation, we use extended non-negative real numbers as truth values, and then postconditions and preconditions can be regarded as functions that represent expected cost. And now we can define the weakest precondition for expected cost by computing the expected cost backward. So that is from a function from a function for output to a function for input. Okay, and let's look at another instance. So here we consider a program that output strings. And the problem here is given a program and a finite automaton, we want to verify that any output string is accepted by the finite automaton. And in this case, we use a set of states of the finite automaton as a truth value. And then we can define the weakest precondition by considering a backward runs of the finite automaton. So, and this weakest precondition is useful for solving the current problem because we can compute the set of possible initial states from a set of final states. Okay, so we have seen many instances of weakest preconditions. And so now, we want to know how to uniformly deal with various kinds of weakest preconditions. But actually, there's existing work on this topic. This paper proposed a general category-theoretic framework for weakest preconditions. So I'm going to explain this. So the instances of weakest preconditions that we saw can be summarized like this table. So in general, we consider programs that may cause computational effects, and it is well known that computational effects can be modeled by monads. And next, we used truth values that are not necessarily Boolean. So we write a set of truth values as omega. And finally, when we define an instance of weakest preconditions, we need to define an action of computational effect on truth values. So, for example, when we define the weakest precondition for total correctness, divergence is mapped to false. So this gives what I would say, an action of computational effect on truth values. And using category theory, we can capture this as an Eilenberg-Muir algebra on omega. So, in general, the weakest precondition is defined for each combination of a monad, a set of truth values, and an Eilenberg-Muir algebra on omega. So this is the definition of generic weakest precondition proposed by this paper. So, given a program and a postcondition, the weakest precondition is defined by this composite. Here, T is a monad that represents computational effect. Omega is a set of truth values, and nu is an Eilenberg-Muir algebra. And in fact, all the instances in this talk can be obtained in this form, in this way. Okay, so I have explained the existing work on semantics of generic weakest preconditions. But please note that this work is about semantics of generic weakest preconditions. And what we want to know here is the syntactic counterpart of the generic weakest preconditions. So why, we want a syntactic counterpart because, as I said before, a syntactic computation would be more convenient for program verification. Then, what exactly is the relationship between the existing semantics and the syntactic counterpart that we want? The relationship can be depicted like this. So, in this diagram, the upper half corresponds to the syntax, and the lower half corresponds to semantics. And we have a mapping from syntax to semantics, which is called an interpretation. In the existing work, generic weakest preconditions are defined in the semantics part. And what we want to know is the syntactic counterpart here. And it is expected that the syntactic weakest precondition and the semantic weakest preconditions are equal up to interpretations. And we show that a CPS transformation is the syntactic counterpart of the generic weakest preconditions. And this gives the first half of our result. So now I'm going to explain the first half of our result, which is a general theorem. Our general theorem states that generic weakest preconditions can be computed by a CPS transformation. But before explaining the CPS transformation itself, I'd like to explain the input and the output of the transformation. And the input for the CPS transformation is a program that we want to verify. More concretely, we consider functional programs with computational effects and recursion. The syntax is defined like this, and technically this is based on lambda C calculus. But if you don't know lambda C calculus, you can just imagine a programming language like OCaml. And in this language, we use algebraic effect to incorporate computation effect. So in this expression, O is called algebraic operation, and it causes a computation effect. And M is a computation that is invoked after the algebraic operation. And we can deal with many kinds of computation effects in this framework. For example, we can deal with probability, cost, output, and non-determinism, like this. Okay, next I'm going to explain the output of the transformation. And we use formulas as the output. More concretely, we consider a higher order logic with modal operators and a fixed point. The syntax is shown here, and actually the syntax itself is similar to the syntax of programs. The main difference between programs and formulas is their semantics. That is, formulas are interpreted as terms of pure lambda calculus, which is contrary to the interpretation of programs, because programs are effectful. And we don't have algebraic effect in our higher order logic. And instead, this expression is interpreted as a modal operator. And finally, we have a special type, prop, which is interpreted as a set of truth values. In our higher order logic, we have one modal operator for each algebraic operation. For example, for probabilistic branching, we have a corresponding modal operator, which is given by the weighted sum of this form. And also for the algebraic operation for incrementing cost, we have a corresponding modal operator, which is given by addition. And in fact, each modal operator corresponds to the weakest precondition for the corresponding algebraic operation. Okay, now I'm going to explain the CPS transformation itself. CPS stands for continuation passing style. And a continuation is a function that takes output and returns some value. And if we apply a CPS transformation to a program, then the CPS transformed program takes an input and a continuation and returns the value that is obtained by applying continuation to the output of the original program. And the key idea of our result is to use continuations that return a truth value. Then continuations can be regarded as post-conditions. And moreover, if we apply a CPS transformation to a program and pass a continuation to it, then we get a formula of the higher order logic that takes an input and returns a truth value. We show that this is in fact the syntactic counterpart of the weakest precondition. So this is our main theorem. So this theorem basically says that the CPS transformation and the generic weakest precondition equal up to interpretations. In other words, we can compute generic weakest precondition. Yes, thank you. So this basically says that the CPS transformation and the generic weakest precondition are equal up to interpretations. And so, so we can compute the generic weakest precondition syntactically using a CPS transformation. And a nice thing about our main theorem is that our theorem is so general that we can apply it to several interesting examples. So this leads to the second half of our result. So So from now on, I'm going to explain the second half of our result, which is instances of our general theorem. So we obtained several instances of our main theorem, and in particular, we were able to reproduce the results from existing work on program verification, like these papers, and and I would like to say that the result in these papers are developed in specific situations, but they are instances. They are actually instances of our general theorem. So let me explain more about these instances. So the first one is about the expected cost analysis of probabilistic programs. This problem is studied by Avanzini and others. So in this, here we consider probabilistic programs like this. And the problem here is what is the expected cost of such probabilistic programs. And as I explained before, this problem can be solved by the weakest precondition for expected cost. And using our general theorem, we can syntactically compute the weakest precondition for expected cost. And we obtain this formula. This formula expresses the expected cost of the original program, and actually this solution is the same as what Avanzini proposed. Okay, we have another instance, and here we consider a program that outputs strings, and the problem here is given a program and a finite automaton, we want to verify that any output string is accepted by the finite automaton. And again, this problem can be solved by the weakest precondition, and our main theorem enables us to syntactically calculate the weakest precondition like this. And and this solution is basically the same as what Kobayashi proposed. Okay. So my talk is about to finish, but before concluding, I'd like to compare my work with Dexter monads. So Dexter monads combine dependent type system with weakest precondition transformers. And as far as I know, there are two papers that are closely related to our result. And the first one is the extra monad for free, and the second one is the extra monad for all. And yeah, these books are about CPS transformation and weakest preconditions. However, yeah, this book, this existing work is not sufficient for sufficient for probabilistic programs and non-deterministic programs. So their results are not sufficient for the application like these papers. And this is the main difference from our result. Okay, so that concludes my talk. Thank you for your attention.
Okay, thank you, Satoshi. Do we have any questions? We have a little time left. Yeah?
This is really cool. I'm curious about the DM for free connection on the class of programs on which both techniques apply. Would your technique compute the same kinds of WPs as DM for free does?
Yeah. For deterministic programs, to be honest, I haven't. I guess they give basically the same things, but to be honest, I'm not very sure about that yet. So
do you study the size of the WP that you compute? Are they exponential in the size of the program?
No, I don't.
Because of branching. Does your technique particularly handle branching, or does that not appear in your formalization?
Branching, like conditional branching.
Yes.
Yeah. So in my work, conditional branching. Expressed by a case analysis. So.
And does it end up being exponential in size? Or?
I guess no.
If you inline the continuation in each branch, you end up exponential.
Yeah, that's true. Yes. So when we apply the CPS transformation to this expression, we need to insert a continuation for each branching.
Okay, thank you.
Any other questions? Then I had one last question before the break. It seemed like actually your treatment of notion of truth values was very general, right? That ultimately you didn't. Am I right that there wasn't actually an ordering or anything required on the truth values?
Ordering. We do require ordering on truth values.
Okay. Okay. Well then, I misunderstood. Okay. Let's thank Satoshi then. Yeah. And then let's have a nice break.